This section will provide an overview of what is required for metallographic specimen preparation. First of all, what is metallography? When I started in this industry about 30 years ago, I was told that it is the art and science of microstructural analysis, and there is a reason why the art comes first. Metallography is not an exact science. However, we will discuss the basic concepts of sample preparation, as well as go through the basic preparation steps required to obtain reliable materials analysis. Metallography can be broken down into 6 basic steps. The first step is to thoroughly document the sample. Since metallography is a destructive testing procedure, cataloging the initial condition and its history up front will save you a lot of anguish later. In many cases, the samples will need to be cut to either reduce their size or to approach the area of interest. Section can be the most critical process, so proper cutting should minimize the amount of microstructural damage to the sample. After sectioning, it is recommended that the specimen be mounted in a plastic compound for ease of holding for manual grinding and polishing. Also, in most cases, mounted samples will be required for automated sample preparation machines. The most challenging and variable processing step will be the grinding and polishing sequences. This is where there are a lot of differing recommendations and recipes in the industry. What we have done, based on our years of sample preparation testing, is to characterize and classify the specimen preparation techniques into 11 classes based on the material's hardness and ductility. These classes will provide the basic building blocks for properly preparing metallographic samples. After the grinding and polishing operation, the specimen will have a highly polished and damage-free surface. There may not be a lot of features visible to the eye or with the aid of a metallographic microscope at this point. This is where the true art of metallography can be found. What is most commonly done is to etch the specimen in order to selectively bring out the microstructural features. Once the features have been enhanced, examination is mostly accomplished with metallurgical reflected light microscopes or scanning electron microscopes. However, there are a lot of ways to characterize the specimens depending upon the requirements. Depending upon the documentation requirements, quantification of the basic metallurgical ASTM standards can also be accomplished and documented with image analysis processing software. To truly understand what is required for metallographic specimen preparation, it is crucial to have a knowledge of the basic properties of the material being tested. The following chart plots the most common types of materials based on their ductility and hardness. Ductility is based on a material's brittleness or toughness, and hardness is classified as either soft or hard. How a material's microstructure will respond to cutting, grinding, and polishing will be directly related to these mechanical properties. Class 1 materials are softer and more ductile. Examples of these include aluminum, copper, lead, and zinc. Class 2 encompasses very soft and ductile materials where abrasive embedding can be a problem. Examples include rhenium, niobium, gold, and silver. Class 3 covers medium soft and ductile materials. Examples are powder metallurgy parts and cast irons. Class 4 materials are characterized as soft and brittle nonmetals. Examples include silicon and gallium arsenide semiconductor materials and other electronic nonmetals. Class 5 are medium, hard, and ductile materials such as low-carbon steels and stainless steels. Class 6 covers harder and tougher non-ferrous materials such as titanium and other superalloys. Class 7 thermal spray coatings are hard coatings on softer substrates. They are essentially hard materials with moderate ductility. Often, these materials are used for wear and thermal resistance. Class 8 represents heat-treated and hardened ferrous alloys. Class 9 materials are characterized by high hardness and high ductility. They are often engineered materials such as metal matrix composites. Preparation can be tricky due to wide variations in the individual component properties. Class 10 properties include the tougher, very hard engineered ceramics, such as zirconia and silicon nitride. Class 11 are very hard and brittle materials. Examples include glass and mineral specimens. With a basic knowledge of the material's properties, let's now take an overview look of the specimen preparation steps. The purpose of abrasive sectioning is to cut to the area of interest. The goal is to minimize the amount of microstructural damage. It is important to note that it will be time well spent on this step to minimize cutting damage, as there are cases where no amount of grinding and polishing will be able to eliminate excessive microstructural damage. The two main types of abrasive sectioning are with an abrasive blade cutter and precision wafering saws. Mounting may or may not be required. However, in most cases, mounting can make the specimen preparation process much easier. The main reasons to mount a specimen are for easier holding and to protect the critical microstructural features. Mounting is done with the aid of compression and temperature mounting presses, as well as castable resins, sometimes erroneously referred to as cold mounting resins. In many cases, rough grinding with today's more advanced polishing machines is not required. However, if you cannot cut close to the area of interest, belt grinders can be used to efficiently grind to the area of interest. It is highly recommended that a belt grinder with a squaring fixture be used. Otherwise, a lot of secondary rough grinding may be required. Note, rough grinding may also be required if the samples were not cut properly to begin with. Fine grinding is accomplished basically with a stepwise progression of finer and finer abrasives to eliminate the previous step's damage. This damage can be to both the surface and subsurface layers of the microstructure. This process is commonly done with manual or automated grinding machines. Polishing is the final mechanical preparation step. The goal after this step is to have eliminated all the surface and subsurface damage. The process is easier with automated polishing. However, it is not uncommon for skilled users to manually polish the specimens. Additionally, by far the best way to final polish a specimen is with vibratory polishing. Vibratory polishing gently abrades the surface layers without introducing subsequent damage. Often, vibratory polishing also uses CMP or chemical mechanical polishing abrasives to enhance the polishing process. Etching is where the real art comes into play for microstructural preparation. It is used to reveal the microstructure for highly polished, damage-free specimens. Etching is accomplished via chemical, electrochemical, electrolytic, thermal, magnetic, and other more specialized techniques. Once the specimen is prepared, the next step is to evaluate the microstructure. Since the majority of metallographic specimens are reflective, a metallurgical microscope is required. For these types of microscopes, the light is reflected off the surface, and depending upon the optical setup, the microstructural features are revealed. Quantitative image analysis based on ASTM standards can also be obtained and is very easy with today's computers and software. The results for metallographic testing provide a means to monitor quality control and to determine why something failed for future product improvements. Metallography is certainly a very powerful tool.